Geez, we're live, people, and that's good. LeetCode on a fluke, day 14, and we have this little club where we practice solving algorithmic problems, and we have a problem here, an algorithmic problem to solve. It's called this. I'm going to share it now. So it took me some time to understand it, and we have 30 minutes till we have a session with our club. And I'm going to try to see what I can do in the 30 minutes live. Before that meeting of our club. So this is count the number of good nodes. Good node. And okay, we're given an undirected tree. So that means we can go from not only from top down, but we can go in any direction. It's not and it's given in a two-dimensional integer array of edges, and we have the rule is node is good is if all of its subtrees rooted at its children have the same size. Size is the number of nodes, and we need to return the number of good nodes in the given tree. A subtree, yeah, okay. So, and in this case, all of the we have a node 0, and it has a by the way, where is our timer? Okay, timer, and it has a root. It has two subtrees, okay, and these subtrees have size 3, so number of nodes in them is size 3, so they're the same. That means this node 0 is good, and the same thing happens with others. Now, in this example, so the leaf has exactly the same size of its subtree, so they're all 0. So all of the leaves have that. So 3 has two subtrees, and they have the same 0 length, the same size 1. And now node 2 has two subtrees, but one of them is size 3, and this one is size 1. So 2 is not a good node by the rules. In this case, we have this node 0 has 3 subtrees, and notice this is not a binary tree, so there could be more nodes than 2, more children than 2 for each node. So it has 3 subtrees, 3 children, and each of this one has 4 nodes. This one is 4 nodes. This one is 4 nodes. They all have different structure, but the number of nodes is the same. So that's why 0 is a good node. So 5 is a good node because it has only so all of its children have all of its subtrees have the same size and it has only 1. So 10 has only 1 subtree. 9 has 2 subtrees. 9 but they're different size, so 9 is not a good node. 1 has 3 subtrees of the same size, so 1 is a good node. So this is kind of the problem, so the number of nodes is the key, not the structure. Okay, and the important thing, we can go from any node. We can kind of have this adjacency array. So from any node, like from node 1, we know that from node 1 we can go to, so its children are 3 and 4, but we know that from node 1 we can also go to 0. We can go to 0 because we know we can find 1 in its adjacent, in its parent in this case. Yeah, so we have that information. Not in constant time unless we record it, rewrite it in a map or something, but we do have it. Now, okay, so how do we do that? I mean, like, what do we do? Let's at least think about some logic. So we need to know to tell. Okay, brute force. I don't see like immediately a perfect solution. Brute force would be to look at each node. Brute force solution, I mean. A brute force solution could be take a node, look at its subtrees, and check their size. Okay, there is probably a function to check the size. We can traverse the subtree and learn the size of its size. Then we'll remember that, and we'll count that. And it's probably going to be for each subtree, counting them is at least linear. Yeah, it's probably going to be linear. We need to go depth first search. Yeah, and as long as we don't go to the parent, yeah, we can check and see that the number of, yeah, it's a linear operation. So for each node, we'll count all the sizes of all the subtrees, which is n square, which is, in our case, and number of nodes in our case is 10 to 5 to the power of 5. Edges length is n minus 1. Edges okay. A, B. The input is generated such that edges represent a valid tree. Okay, so it will be 10 to the power of 10. So n squared will be that, and which is kind of too much. So how can we make it better than n squared? And we could use some memory. If we just record once the size of each subtree, so we'll get to 12. We know that 12 is 1. Then we'll we'll add for 9 we'll yeah, if we go by the leaves first, we'll know that will be this type of traversal where we check first its leaves, and then we go to the node. If we do that, it's called, by the way, I even know how it, it's the post order. Yeah, we'll check all the nodes. That way we can first count the nodes, and then we'll know. So for this node, we'll check the node and we'll know. Yeah, so we record the size of the node, okay, of the subtree. So I guess that's kind of the solution. Yeah, we'll record the size of the subtree in a map, or we could also use some kind of mapping data structure to record the size of the tree. Yeah, we can, or we can even use an array with the but okay, it's a different question. And if we know the sizes, so it's a linear, so it's constant time operation to know the size. So next time we traverse the tree, we need to check each node. Check each node. By the way, if we do that, if we have the number by going post order, we have the numbers. We will be finishing them anyways. I mean, and by the way, the number of children could be pretty big. So we at least need to remember for this specific node, not just the sum, but also we need to, we need to track the sum, but also we need to track if the nodes had different or equal size. Yeah, if they are of the same size. So that way we don't even have to remember it. Because, so we'll get the sum, and so in each call we need to, we'll just track them. So if, it looks like, we might not even need the memory. So it looks like the solution is about the, if I'm not mistaken, it's about this post order traversal, which means we'll go and will be DFS node left, not left. We'll be going over the nodes first, and then once we're done with the nodes, and while we will be doing that, we'll be comparing, and we will be tracking the number of good nodes at the same time. So so the way it will go, okay, we'll start with this node. There will be a call for this specific node. This node will start a call, so a recursive call for its children. Its children will start recursive calls for its children. So this child number 12, child with value 12, this will also start, and it will get its size. Yes, it will know that it's a good node. We'll count that, but it will also remember its size. And so in that call for 9, we will be doing that. Then 9 will call 10. So 10 will recursively call its children. And it will be 11. 11 will remember its, also check it, so it will be tracked as a good node. And 10 will also determine it's a good node, and it will return its size. So we need, from each node, we need one thing, two things. Okay, we need to track the number, and we need to track so this is called so this is good nodes. Good nodes will start with 0. Good nodes count. And it's a post order, basically. Post order. I'm not sure it's gonna be a quick, an easy, a short solution. Might be. So we need to track that. We need to track. And what else? I mean, but the thing is, we have edges. Edge. So will be A, B, and array of length where indicates that there is an edge between nodes A and B in the tree. So that means, and I mean, edges could be, it doesn't say they're sorted. So it doesn't say they are. But I mean, could we just go because I don't want to do the search every time on every node, because there could be anywhere, and we'll have to search the entire array each time for each. So node A has nodes. This node has 1 and 2. So we will, just to find that, we will need to go over to loop over the array. And that's kind of it's kind of a lot. I mean, that gives us again, that gives us n squared, right? Because for each node, we'll need to find its children. Then for each child, we'll need to find its children. So if we we also want to start with We want to start with what? Do we want to start with any node? Because here is the deal. We don't have to go just in one direction. You remember, I haven't been dealing much with undirected trees though. It's a graph, okay? It's a graph. So I mean, from any child, we can identify its parent. Looking at, if we get any child, we can identify its parent. So there might be even an easier solution to that. That's what I'm thinking. We see a node, but I mean, we want to go in some kind of organized way, organized fashion. But if we just get any node, like, okay, there's this node 1, and we'll start going from this one. Yeah, it seems a bit chaotic. Like, why would you start with this and just go just from a random node? That's what I'm thinking. But at the same time, trying to understand, okay, why is it better? Why is it? What's the value here of having it undirected? It's kind of, I don't, because there should be, and I don't see it immediately. Usually, it's important. I mean, usually it's helpful when you need to get to the parent. But if we are doing post order, we will be, in each call, we will have the parent on our in our state. Yeah, within the call. Yeah, call context. Yeah, not state, but context. Yeah, of this call, we'll have the parent. But what if there is an easier way? That's what I'm thinking. Knowing that we already have that they are what is it called? Undirected. Yeah. The fact that it's undirected, and could we just, I mean, could we just go over this without without having to like do anything else, like creating a map of node with its children? It will be it will be an ON extra memory. Yeah, there's probably, I'm pretty sure there is a reason for that. Otherwise, I mean, we could just, representing a graph like that using structs. You see, you can have a struct where where its children there will be an array of its children. Okay, so that way you can have flexible number of children, not just two fields for left and right for a binary tree. So I still feel like the simple solution is to create a map. Okay, so our solution right now is to create a map. And in that, creating a map for each node. That map will has its children, an array of its children. So the key will be the node, and that way for each node we can, in constant time, amortized constant time, get all of its children and do our post order. Yeah, I think that's the thing. It's what if there's another way to do it? What if we go from bottom up? For each child, we create a map of child to map of his map of child to parent. As we know, each child has only one parent, so it's kind of, but yeah, and there is, by the way, are the values unique? Each child has only one parent. Parent has several children, but I'm not sure if they are unique. A and B. I'm pretty sure, I would expect they are unique, the values. It doesn't say so. It doesn't say so, but I kind of intuitively think they are unique. In that case, yeah, we can create a map like that, and then we'll start. So that will give us all of the nodes with its children. There will be one node that doesn't have any children, though. So that's the root. Otherwise, yes. But what will that give us? We will get that. Again, we will have if we know which of them are leaves, so that means they don't have any children. Like this 12 is a leaf, and we could start with the leaves. We know their size is 1. We count them, count the leaves, and it's pretty obvious. Then from the leaves, we will go to their parent, and we will and I don't know how to do that. So it's kind of, we have this, yeah, because we need to have in the context of that node, we need to compare the sizes of these trees. in the constant context. So we need to have some kind of a comparison, run this comparison in one call. It's good to have this, we have this node. So that requires us having the map from the other direction, that requires us to have a map of parents to children. So then we'll check out all of its children. Yeah, I mean, we can have that map as well, and we'll go from the children. Let's say from so. But I mean, it's pretty much we can do it in. I think it's a post-order thing. Yeah, we have a map. We'll make a map, with parent, child. It will be integer, but it will have a slice, so it will have children. So we'll know that 0 has a child of 1. Okay. Yeah, and I feel it's like that, but I need to drop and get onto our club call. But I think we kind of got the solution for this one. So thank you for watching. Like and subscribe, and we'll see you in the next video.